So this next unit is actually a very large unit, and I've decided to split it into 3 mini units, but it covers all of the same kinds of concepts. We start off with basic equilibrium, then we'll move into acids and bases, and then last into things like buffers. So first up, Le Chatelier and chemical equilibrium. So chemical equilibrium, that is really hard to say, is when you have a reversible reaction and the forward rate equals the reverse rate. And it seems like the reaction has stopped, but it really hasn't. We're still making products, we're still making reactants, it's just the concentrations no longer change. We call this dynamic equilibrium because things are still moving in both directions. And we do use that double arrow to represent equilibrium. So you really should pay attention to arrows. If you have one arrow, it goes to completion, that arrow, equilibrium, and it does result in some different math. So what does this graph tell you about equilibrium? Well, recall that slope tells you rate. When it's really steep, the reaction's going fast. So when you get to this section here where the graph flattens out, that's equilibrium. And even though we're still making products, we're still making reactants, the concentration no longer changes. You need to know that. Now, a lot of students think that equilibrium is where these two lines cross. That is not the case. It's where your slope goes horizontal, there's no longer any change going on. And we're assuming that nothing is escaping from the system. It's pretty easy to write an equilibrium expression. And just remember that there's lots of different Ks. There's Kc, there's Kf, Ka, Kb, there's just tons of K. It doesn't really matter at this point, equilibrium. So if you have some generic equation of this, A plus B makes D and E, where the big letters are whatever the chemicals are and the little letters are the coefficients, it's simply products divided by reactants. And you take the whatever the chemical is and the coefficient becomes the exponent. Kc only depends upon the reaction and the temperature and not the mechanism. Remember that we use brackets to show molarity, and there is no label for K. Now, I thought it was just for simplification, but I learned in one of my graduate classes that here's the reason why. It's not actually the concentration of D in this case. It's actually the ratio of the concentration of D to the concentration in its standard state. Well, the standard state for solutes is 1 molar. So really, that concentration D is the concentration of D divided by 1 molar. So the molars cross off and you don't have a label. Kind of cool. Just know that we can also do this for gases. Instead of Kc, we're going to write Kp. And notice we don't use the brackets anymore because we're not dealing with molarity. We're just dealing with pressure, either in atmosphere, bars, or whatever your book likes to use. So we just use parentheses, but the same rules apply. There is a great equation that relates Kc and Kp, and it's right there where the change in N is the change in moles. You have to look at what's going on in the reaction. It's the moles of gas produced minus the moles of the reactants. So the value of K is actually pretty important. It lets you know where the equilibrium lies. In other words, do we make lots of products or do we not make a lot of products and stay in the reactants? Just think mathematically what's going on here. It's products divided by reactants. So how do you get a really big K value? Well, you've got to have a lot up here. You have to have a lot of products. So a really big K value means that the reaction goes forward more than the other direction. We make a lot of products. But if you have a really small K value, that must mean your denominator is really big. In other words, we have lots and lots of reactants. It just doesn't tend to go, and we wind up staying in the reactants. Because these reactions are reversible, if you write a K expression for a reaction and you want to know what the K expression would be for the reverse, it's just the reciprocal. Literally just take your expression and flip it over. That's it. That easy. Well, so far we haven't talked about different phases. And you need to know what's in the red on this slide. Whenever a pure solid or pure liquid is involved, we do not include it in the expression, only aqueous and gases. Why? Well, because the concentration of a pure solid or liquid has a constant value, and we're only going to put in values that can change. And then there's something else called the activity of any pure solid liquid is always 1. Well, we're not going to discuss activity necessarily in this class, but just know that everything that we're talking about is actually more complicated than we allude to. What actually can happen in solutions is something called ionic strength. And so sometimes we get results that we wouldn't often expect. And in advanced classes like analytical chemistry will take into account activity coefficients to help account for this. It basically is a measure of how much behavior deviates from the ideal. And if ideal behavior occurred, you would have an activity coefficient of 1. Well, pure solids and pure liquids behave ideally, so we say that they approach unity. In other words, the concentration equilibrium is ideal. So just know that we don't include solids and pure liquids, including water, in the K expressions, only include gases and aqueous. Well, what if you're asked to calculate K? First, write the expression, pay attention to those coefficients. They need to be your exponents. Plug in what you know and solve for K. Now, sometimes it's straightforward, totally easy like that. Other times we need to use the ICE method. So let's review what ICE is. I'm not going to insult your intelligence and read this whole slide. So just pause it. Take notes, but I'm going to explain how to use an ICE table in the following example. Let's take an example and show how the ICE table works. So here is the problem. You're given a couple of things. You're given the equation right there. You're given the initial concentrations of these two things, and we assume that this has not been created yet, so we just say it's 0. And then they give us how much of this we have at equilibrium. Well, they're wanting us to find K. And so the first thing we need to do is write the expression. Then we have to have all equilibrium values so that we can plug in. Well, we don't have all that yet. So how do we get that? So here's how we do that. The first thing we need to do is to complete our ICE table. Now, if you recall, all we had to begin with were those two values and this value. Well, we need this and we need this. Well, how do we get those? Well, if we started with no HI and we ended with that much, don't we know how much it changed? Yeah. So most students will just say, oh, well then these two things must have changed by the same amount. Now notice they're not the same amount. Why? Well, stoichiometry. This has a coefficient of 1, so does this. This has a coefficient of 2. So you need to do a little bit of stoichiometry, and that's what's here in the purple. And when you do that, you find out that these two things only changed by that much. Also notice that those are negative values. Why are they negative? Well, because they're reactants and we're using them. This is positive because we're making it, all right? So then to find the equilibrium concentrations, you just do what your table says. So it's this minus 9.35 times 10 to the negative fourth, and you get your answer. Do the same thing for I2, 2H, write your equilibrium expression, products over reactants, and don't forget to use the coefficients. That's why HI is squared. Plug in your values, and you get 51. Again, sig figs, which, 6.5 right there. So that's why I use 2 sig figs. We can use equilibrium expressions and constants in another way. One thing we could do is we can predict the direction in which a reaction needs to go to get to equilibrium. We can look and see, are we at equilibrium? Are we before equilibrium? Have we gone too far? Where is the reaction in relation to equilibrium? So we write what's called Q instead of K. It's written the exact same way. And then we just plug in whatever values were given, and then we compare K to Q. And we'll look at that on the next slide. All right, so let's take a look at what we know. We use Q to figure out where K is. And I always use this very silly example that you and your friend K, there's K, are going to go on a picnic. And K has already set up in this beautiful valley between these two beautiful hills. And you are Q, and you need to get caught up to K. Well, if you calculate Q and you find out that Q is less than K, you are right here. You are before K. Well, which way do you need to go to get to K? You need to go forward, okay? If you calculate Q and it's the value of K, well, what does that mean? You're at equilibrium. If you calculate Q and it's greater than K, you've gone too far. The reaction will shift the other direction to go back to equilibrium. So that's a really great way to kind of remember what's going on. But you could also think about it mathematically. If Q is less than K, that's because remember, products divided by reactants. The products up here, there's just not enough of them. So we need to make more product to bring our value up. But I really, really like this expression. This little going on a picnic tends to ring pretty true with students. My son, when he was in college, he always set him up like this, where Q was before K. And he said, Mom, I looked at this symbol right here. And do you see how Q wants to eat K? The reaction's going to go that way. And if the sign is that direction, well, it's going to go that way and eat. Might also work for you. Let's take a look at one more example. For the Haber process of making ammonia, that's the reaction, and that is the Kp, because they're all gases at that particular temperature. Well, in an equilibrium mixture of the three gases, we have the partial pressure of H2 and N2. Well, what's the partial pressure of NH3? So write your expression right there. Fill in what you know. Well, we don't know NH3, but we know everything else. And they gave us what K is, so you can set it equal to that. Just do a little bit of algebra and you can get your value for P. What if you need to use the ice method? So let's take a look at an ice problem. So this time we have a different equation. We have H2 plus I2 making 2HI. And we know that we have 1 molar of H2 to start with, and we have 2 molar of I2 to start with. We assume we don't have any of the product. And what do we know? They gave us the value of the constants. So we know that K is 50.5. And they want to know the equilibrium concentrations of everything. Well, how do we do that? Well, we know that it's not going to go to completion because it's an equilibrium problem. So we know that this is going to break it down by some amount X. We know that I is also going to break down by some amount X. Now notice over here we said it's going to break down by 2X. Well, that's because of the coefficient. Every time you break down one hydrogen or one iodine, you get 2 HIs. So at equilibrium, these are our values. Now we don't know what they are, but we want to find them. So if we find X, we could find those answers. So what you want to do is you want to set up your equilibrium expression and plug in what you know and then solve for X. Well, if you actually start doing the work on this one, you're going to find that we have to use the quadratic formula. And the reason why is because this value right here. If this value were a really, really small value, like something times 10 to the negative fifth or negative sixth or negative seventh, we could actually ignore these two little x's right here, but we can't. So let's look at the quadratic formula. So there's the quadratic formula. And so what I did is I just kept doing my algebra. I'm not going to show you right here. And when you solve, you get two answers where x can either be that or that. Well, remember from your ICE table that these are your values. If you plug in the 2.323, you get negative values. We know that's not a solution. So use the other value and you get your equilibrium answers. And if you want to double check, you plug them into your expression and guess what? We got 51, so we did it right. So what does Le Chatelier's principle say in a nutshell? It basically says that if a reaction is in equilibrium and something changes, And that could be temperature, pressure, volume, concentration. It could be a number of things. The reaction is going to shift to get back to equilibrium. So it's kind of like that scale right there. You want it to be balanced. If all of a sudden the reactants go down, you're going to want to bring that back up. So let's take a look at what can happen. Well, we can change the concentration of the reactants or the products. Remember, whatever change occurs, we need to undo it. If we have too many reactants, we need to get rid of them. Well, how do you get rid of reactants? Drive that reaction forward and get rid of them. What if you have too many products? Well, we need to get rid of the products, so we'll run the reaction in the other direction to bring them down. So if you add, you're going to shift away to get rid of them. What if you remove? If you remove product, we need to make product. If you remove reactant, we need to make reactant. You will get practice at this in both homework assignments and in the lab. Just note that the equilibrium constant does not change no matter what you do. Volume and pressure are a little bit tougher, and really there's no memorizing. Just think about it. If they just tell you pressure, that's kind of an easy place to start with, but a lot of times the problems like to have you start with volume. So if volume goes down, pressure goes up, which means we now need to bring the pressure down. Well, how do you reduce pressure? You're going to shift the reaction to whichever side makes less gas molecules. So take a look at that equation. On the reactant side, you have 4 moles of gas as compared to 2 on the product side. So if you need to reduce the pressure, you're going to drive it toward the product side where you're only making 2 moles of product. What happens if you need to increase the pressure? Then you're going to drive it the other way and make 4 moles. So my recommendation to you is when you have volume, think about what volume does to pressure. Volume goes up, pressure goes down. Now you need to bring the pressure up. What do you do to do that? That's what you need to be thinking about. Temperature seems tricky, but really you just need to think about temperature like it's another reactant or a product. So if you have an endothermic reaction, you're going to put heat on the reactant side. If it's exothermic, it's going to go on the product side because you're getting rid of it, you're giving it off. So look at the endothermic. If you add heat, you're adding a reactant. What's it going to do? Shift toward the product. If you remove heat, you're going to shift back toward the reactants to make the heat. Same thing happens with the exothermic. So for heat, just consider it like any other chemical, and whether that it's a reactant or a product, and what will happen if you add or remove it. And all you need to know about catalysts is that they increase the rates of the forward and the reverse reactions. So it's going to make the reaction take not as long, but it has no effect on the value of K. Catalysts do not change K. They just make the reaction go faster.